So, good morning to all. Everybody here in Evra. Today we open a window for the future. Um, and I will try to bring my perspective on the future of the energy sector. Well, when thinking about Conselho today, I wanted to cover what I see is relevant to achieve our target. By achieving the target, I mean having a carbonized society in a few decades. And first, to make the point that of course we need technology and we're developing technology, but we need something else, and I'll get to that. So I will start by some evidence on climate change, science on the trajectory to achieve that, and also proof that we need to accelerate and do more. I will cover five key challenges to address this energy transition. Now, we'll give you one example, namely that will allow us to provide additional speed and settle the portfolio rates towards this direction. And I'll finalize this some final thoughts from my side as well. So let's start. As was already said today, 2024 was the hottest year ever. We were 55 degrees Celsius above pre-industrial levels. Also, we are getting the first statistically significant evidence that the Earth is heating faster than we thought. Also, last years we also peaked on CO2 emissions driven by energy systems, for example. Or, for example, if you look at the top 10 climate disasters that happened, the direct cost of these disasters was in the range of 230 billion euros. So it's just to reiterate that this is a big problem that we need to address. Well, there are many pledges and targets, and these pledges and targets that have been set globally would put us at around 2.1 degrees Celsius in above industrial levels, which is already bad. But again, the point is that if you look at concrete action, concrete delivery of these pledges and targets, this may put us in this trajectory to 2.0 or 3 degrees Celsius above industrial levels, which is even worse. And this means huge climate and physical impacts, as well again was already said today, more frequent extreme heat, droughts, wildfires, you know it, and of course economical impacts as well. So 15 to 34% of global GDP may be at risk if you follow this trajectory by 2100. And this is the I kept organic, so economics matter to me. So and many times for decision makers, we need to show these figures because this really means almost destroying 1/3 of wealth if this is to take place. And this means also 13 to 36% decrease, for example, in yield in agricultural crops, or we will not be able to use, for example, we'll be using less 2% of our time to work, as we will not be able to work because of heat, for example. Or we will be spending immense amount of money to recover from disasters, rather than spending that money in productive activities or creating value. No, and I come from the infrastructure company side, and the infrastructure companies are the ones that will suffer the most. Electrical companies, telecommunication companies, because we have assets spread all over the territory, and we will suffer from these, let's say, previous disasters. And I think it's we can say that around 20% of our EBITDA or our gross profit is at risk because of this. I mean, we just saw recently in Portugal, end of January, stores that hit our territory, and the huge impacts that they have. It's a picture by one of these storms that hit Portugal with. Well, the world has realized in 2025, $2.3 trillion were spent in implementing the energy transition. Almost 40% in electrical vehicles, 30% in renewables, 21% in grids, and by the way, 35% of this done in China. But the other conclusion is that we need to multiply by 2.3 times this investment every year between now and the following years, if you want to achieve those targets that I was alluding to. And this means multiplying by 2 or 3 electrical vehicles, renewables, grids, energy storage. And as well, other technologies like CCS which means carbon capture and storage, or some nuclear technologies as well. But I mean, the energy transition is really trying to change this entire system. It's in a few decades, something that took us 150 or 200 years to consolidate, and we need to do in a few decades. So this represents a bigger challenge. We know we have this problem. We know we are, let's say, on a trajectory to try to solve it, but we need to do much more. And there are several technologies that will allow us to do this. We have technologies which are already quite mature, like solar or wind or batteries or electric vehicles, which are already quite mature and which are already quite impactful. There will be other technologies which are less mature by now. For example, let's say on the ends of this maturity spectrum, let's say, topics like small modular reactors or fusion technology or some other technologies, emerging renewables, etc., which are may also be playing a role. But the point is that by focusing on 15 technologies alone, 15, we will be able to solve 70% of the emissions reduction that we need to do by 2008. These technologies are ones that we already know: solar technology, onshore wind, offshore wind, batteries, electric vehicles, heat pumps, some heat electrification technologies. So these 50 technologies alone will allow us to solve 70% of the problem. But my point is, technology is not, or inventing new technology is not really what I think is most relevant. So we usually present these 5 challenges that address which are relevant. Of course, they involve technology, but the topic here is not technology. And these challenges are: one is speed and scale, the other is policy and incentives, the other is labor, the other is customer adoption, and the other is the supply side. So I'll try to address each of these challenges. Speed and scale, as I said, we need to accelerate and to be able to deploy at scale all the assets that are relevant to this energy transition, be it grids, renewables, energy storage, electric vehicles. And so we need to do something different. We need to design faster. We need to build faster to be able to have to achieve this this pace that we need to. Well, to do that, we need to use new technology and to do things differently. Also relevant to that acceleration is policy and incentives. We need new market designs. We need new regulation schemes that allow us to have sustainable investment flowing into this arena. We need streamlined permitting to be able to deploy grids and renewables. I can give you an example. I don't know if you know. Do you know how much time it takes to full permitting of a wind farm a year? It's 6 years. Still 6 years. Or for example, if you look at United States, which usually is a proxy for simplification, to have full permitting of a solar farm, it takes 3 years. The only exception to this is China. But China, as we all know, plays with different rules. So in China, you can do full permitting in less than a year. But I mean, even if we can't get that far, I mean, I think we all can agree that we can do something to accelerate permitting of these wind farms and solar farms, as an example. Labor. The energy transition is a labor-intensive thing. For example, when we had 2 coal plants in Portugal, we had 2 gigawatts capacity. To achieve that same capacity, we now need to have, if you consider, let's say, the average size of a solar plant, we need to have 400 plants. So 400 interconnection points. So 400 substations. So it's really demanding in what regards to labor. And learning, of course, there is lots of opportunities, but there are some estimates that say that we will have a 7 billion people get by 2030 to implement this energy transition. So again, we need to look at technology, train people, but all this together to be able to circumvent this language. The other challenge is customer adoption. So all technologies need to be designed for adoption, for client adoption. It's me and you that take a decision whether or not to install a solar panel on our rooftop. It's me and you that take a decision whether or not to buy an electric vehicle. Me and you that decide whether or not to electrify an industrial process. And so we need to take these decisions, and technology need to be prepared for us to take these decisions. So we need to be able to sign long-term contracts to implement this. And so we must think adoption first. And finally, supply chain. So supply chain is of course an issue. We are moving from, let's say, from a geopolitically constrained fossil chain to a, let's say, also geopolitically constrained mineral chain. And I mean, we must acknowledge that and we need to take decisions in order to navigate that. Of course, we cannot also avoid China dominance on the energy transition. And I guess in average, China dominates 70% of all the relevant things to implement energy transition: photovoltaics, wind, batteries, hydrogen, heat pumps, electric vehicles. In average, around 70% is dominated by China. So again, we need to embrace that with partnerships and understanding what we need to do with China, but as well hedging in order to mitigate this risks that this also entails. So, well, maybe we're too far. But anyway, we have robots. We understand. We know that technology will play a role, but as I mentioned, I mean, this factor to speed up and scale up the deployment of technology is quite relevant. I don't know, what you can see here is a 4T. I guess everyone knows what's 4T. 4T was this model implemented by Ford motor company like 10 years ago. And at the time, Ford wanted to put many cars on the streets. They even came up with this slogan, which was, "You can have a technical light provided it's flat." But then, anyway, it became phased in each study in business schools because it's like a proxy for industrialization. So they have to take decisions in order to be able to speed up the deployment or the industrialization of all of the cars. And they did just that. And in 4 years, they reduced 87% the time it takes to build a vehicle from 12 hours to 1.5 hours. And so since then, they became a reference. And I guess the point here is that we need to find our 4T for renewables and for grids. I'm not saying that we want technology alone, likely the combination, but we need to find our 4T to be able to streamline, to accelerate, to speed up this energy transition that we are developing. So let me give you an example from grids. So on grids, we need to install 100 billion kilometers of grids until 2050 to be able to deploy this energy transition, and we multiply by 2 the phase at which we are investing anyway on grids. And we have several other issues like the cost and availability of materials. I don't know if you know, but transformer, which is a key piece in energy system, has 2 to 3 lead time now. I mean, you can order the transformer if you order it now, you get it 2 years from now. And also labor shortage, for example. But so it's a huge challenge grids are undertaking, and international energy is saying that grids must not be the bottleneck, etc. We all know that. But really, so grids have every challenge. So let me start with overhead lines. The way we usually build an overhead line is, I mean, we survey spots, we dig some holes to install foundations for the poles, we install the poles, we load the equipment, the carriers and the equipment that we need to load, and then we do the assembly. To do this, let's say for an average size line, this takes 5 to 8 weeks, 5 to 10 full-time people doing the job, and it takes us like 1 to 2 weeks working at heights, which also implies some risks. And so the question we're asking ourselves is, I mean, why we do it this way? Can we not do it differently? Can we not streamline this process? Um, and the answer is yes. So regarding overhead lines, following all, let's say, our working innovation side with our grids business, we can conclude that by just using modular foundations, which are precasted and then just assembled on site, composite poles, which are much lighter and can be transported easily and brought to place more easily, and also using drones to defect equipment and to pull some cables on our overhead line, you can reduce 60% construction time and increase 2.2 times the, let's say, development rate that they can, or the development capacity in our areas. And what about the underground lines? So underground lines, when we typically do it, it's not so different, but also survey the spot. We open a trench. We load the equipment that we need to cable and the equipment that we need to install on the trench. We assemble everything, we test, and then we close the trench. And to do this, it takes us, well, here the range is big, but it takes 2 to 15 weeks, 5 to 8 full-time people. And again, the conclusion is not so different from overhead lines. Is that if we use some technologies which are, let's say, not rocket science, like using GBR, it's a georadar, so technology that allows us to scan the soil in order to find the infrastructure, and also instead of opening trenches, just opening small holes and then using directional drilling to install our cables. With this, we are able to do 72% the construction time of our underground lines, and with 18% the layer that we need to implement that. Of course, with some other benefits in both cases, like reducing costs, reducing CO2 emissions, mitigating risks. Well, but this is what else that we do. This is just a quick example from China. This is from State Country. And this is basically showcasing the some robots doing some works on lines. This is basically assembling 2 robotic arms on top of the brain, and they are doing these works under voltage. And this is basically a way to increase productivity, as well to mitigate the risks, because we are working at heights and we are no longer work under voltage. So this is an example, and also to say that we are exploring AI and robotics, and trying to match those technologies with the best use case to do with this energy transition. In our labs, we have what we call this, let's say, enabling technology, robotic arms, drones, these robotic dogs with some sensors and that can do some triggers and activities. And we are adapting them, customizing them to be able to do some of these use cases. Well, I need to conclude. My time is now good. I needed to conclude with something, which is I asked AI to generate this future vision for the energy system that I just chose. I'm not sure if you are ready for this, but I will show you what the AI does to me, and this is it. I was extending the wall. No, but no. This is exactly the opposite to what I think. My point is that we don't need to invent more technologies. Of course, technology plays a role, but I think it's much more efficient, more effective if we unite our efforts in making sure that we're able to create conditions to scale up and speed up the deployment of solar, of wind, of power grids, of energy storage systems, and by doing that, we address the bulk of the energy transition. Thank you very much.